In this chapter, we will learn the dynamic properties of the soil and how to describe these dynamic properties. And in this chapter, we have 4 parts. The first is the dynamic properties of soil, deformation, and the parameters. Then chapter 2 and chapter 2 is dynamic behavior of Visco-elastic model. In order to describe the dynamic behavior of soil, then we try to use some viscous and elastic model. We combine them together, then create a new visco-elastic model to describe this kind of dynamic behavior. And part 3 is dynamic behavior of plasto-elastic model. And we can also use some plastic model and elastic model. We connect them together, then they will show some plasto-elastic behavior to describe the dynamic behavior of soil. And in these 2 parts, part 2 and part 3, in fact, we only described the theoretical properties of this model, visco-elastic model and the plasto-elastic model, but haven't used them directly in the soil. It's only a foundation. It's only a foundation to develop some real constitutive model to describe the dynamic properties of soil. Then in part 4, we will try to develop some visco-elastic constitutive model of the soil. Here we call it visco-elastic constitutive model. In fact, it's a real visco-elastic constitutive model. And the parameters of this kind of model, including the stiffness and damping ratio. But in fact, they are composed by some viscous model, elastic model, and the plastic model. When they connect together, in fact, they only behave like visco-elastic material, then we call it visco-elastic constitutive model, but not a plasto-elastic model. And in soil dynamics, in fact, a plasto-elastic model is same with the normal soil mechanics. For example, Cambridge clay model. That's a plasto-elastic model. And we introduce this part in advanced soil mechanics. Then we will not introduce a real plasto-elastic model of soil in soil dynamics here. Okay, then let's move to the part 1, dynamic properties of soil, deformation, and parameters. First, before we want to know the dynamic behavior of the soil, then we must know the properties of soil, not in dynamic load, not only in dynamic load, but in all kinds of load, steady or dynamic load. What's the properties of the soil? Then, in fact, it's a review of soil mechanics. Let's see those properties. The first is non-linear and non-elastic. we know that when we apply the load on the soil, then the relationship between the shear and the stress, the stress and the strain, the relationship between stress and the strain is nonlinear. It is very clear, and we do know these properties. And another is non-elastic. We know that when we walked on a soft soil, then we will leave footprints on the soil. That's the deformation, the vertical deformation due to our body weight. And this deformation cannot recover. Then this deformation is not elastic deformation, and the soil is non-elastic. Second is strain hardening and strain softening. Strain hardening, and for loose sand, for example, for loose sand, when we applying the shear force, shear load on the loose sand, then with the shear strain developed, the volume of the loose sand will decrease. That means the loose sand during shearing will tend to dense. If the loose sand tend to dense, then the stiffness will increase. Then we call it strain hardening. This is only example using loose sand. And for clay, for other kinds of soil, we can also observe this behavior. Another is strain softening. For dense sand, when we apply the shear load on the dense sand, then with the shear strain developing, the volume of dense sand will increase. That means the dense sand during shearing will tend to lose. If the dense sand tend to lose, then the stiffness of soil of this dense sand will decrease. That means the dense sand tend to soft. Then we define this phenomenon as a strain softening. And we also can observe this behavior in other kind of soil. Okay. Then the third is the shear compressed or shear expansion. It's same with I explained just now. With the shear load developed, the volume of loose sand will tend to will decrease. That's shear compression. Or for the dense sand, with the development of the shear load, the volume of dense sand will increase. That means it tends to lose. Then we define it as shear expansion. Okay. The fourth is fractional material. Strength depends on confining stress. We know the soil, for the soil, is many soil particles get together. Then the deformation of the soil is just the soil particles deformation relative to the neighbor one. And if the soil want to move relative to the neighbor one, then it must overcome the shear strength in the joint surface between these two soil particles. And this shear strength, like a fractional material, if the normal stress is higher, then the shear strength is also increase. That means the shear resistance depends on the normal force. And the normal force just depends on the confining stress. For example, when you take a piece of soil in your hand, if you hold it tightly, then you use another finger to push it. Then you can find this soil is hard. But if you release your finger and you use another finger to touch the soil, you'll find the soil is so weak. This holding force is just the confining stress. The strength of soil just depends on confining stress. Is a behavior of a fractional material. Fifth is stress part. We know in soil mechanics, usually the stress parts will affect the result, the deformation result of soil. That means the behavior of soil depends on the stress part. For example, from one state A to another state B, and the shear stress is not same, and the normal stress is also not same. And we can first apply the normal force, then apply the shear force. This is one stress part. Another way is first we apply the shear stress and then apply the normal stress. This is the second part. Comparing the deformation with different stress part. Although the stress state tend from A to B, but the deformation totally different. We know that if you apply the shear first, then apply the normal stress, then it will cause larger deformation. But if you first apply the normal force, and then next stage is applying the shear stress, then the deformation is not so much. That's the effects of stress part. And the next is mid-principal stress, direction of major principal stress. And in Traxel test, we learn soil mechanics. We know Traxel test is a very important test in soil mechanics to get the relationship between the shear stress and the strain and get the shear strength of soil. And for the Traxel test, we will make a cylindrical specimen, soil specimen. Then applying the confining stress on this cylindrical specimen. Then we can find for the surface of cylindrical, there's a two direction in the normal direction, x and y. But another direction is a vertical. Usually we use z. And when we use Traxel test, the sigma 1 and the sigma 2 from x direction and y direction are same because we use water to apply this pressure. That means usually we will have three directions of the stress, x, y, z, two horizontal and one vertical. Then only larger one and the lower one, because for horizontal two stresses they are same. then there's no different. We couldn't find the mid principal stress in traxel test when we use cylindrical specimen. But in fact, when we use a real traxel test to make a cubic soil sample, then we can apply the totally different three stresses, larger one and the lower one and the mid one. They are all principal stress if we only apply the normal stress on the surface of this cubic body element of soil. Then the middle principal stress will affect the behavior of the soil. And in recent, we also concentrate on the direction of the major principal stress. We know that when the soil and moving load, for example, a wave load, the wave is will move. Then at a certain point, the vertical stress is a major principal stress, but this direction will rotate, and this rotation will affect the behavior of soil. Next is plastic strain is not normal to the equipotential line. Usually there's a critical line, and in the critical line, the strain will develop normal to these curves, critical curves. But in fact, we can observe in some condition the developing of strain and the direction of strain and the direction of stress are not same. Then isotropic. Now, usually in soil mechanics, we couldn't describe the anisotropic of soil. We take the soil as an isotropic soil. That means in horizontal direction and in vertical direction, soil have the same properties, mechanical properties. But in fact, they are not same. Sometimes they are not same. For example, in the gravity condition, under the gravitational acceleration, the piece of soil particles will sink and connect together. But they have directions, and usually horizontal is the length, longer size of soil particle direction. Then after the consolidation, the soil will create the anisotropic condition. The behavior in vertical direction and the horizontal direction are property of horizontal direction and the vertical direction are different. And another is time effects. And we know in the soil there's pore water, and in the water there are some chemical materials, and after a long time, and this material will create cement between the soil particles. That means they provide a good connection between soil particles. Then, after a long time in the soil, the strength of soil will increase. That's the time effects. And the consolidation status. Finally, is consolidation status. We know that the clay brought to a new location, and there's a new process of consolidation. When we arrive at the new location, first, then for saturated soil,